Hello all, I made a video on the theory of recrystallization, a technique used to purify crude or impure product. Some of my students ran this reaction here, eugenol, which is a phenol, plus benzyl chloride and acid or acyl chloride to give eugenol benzoate. While the two starting materials are not solid, the final product should be. But after a quick water wash and evaporation of the dichloromethane organic layer, the two students whose beakers I'm showing in the cover look like this. You see some crystals, but they are wet or coated with an oil, and I'm going to suggest doing a recrystallization. I'm not showing the final pure crystals because I want my students to discover that for themselves. The first part of this video I want to discuss is what's happening when a product is impure. Well, when a product is impure, you can have inclusion of impurities. And recrystallization helps release those impurities. I'm going to draw a couple cartoons that show crystallization, this process, to exclude impurities. Let's say our eugenol benzoate is represented by these blue squares, and normally when it's a solid, it's going to be a pretty ordered solid. But if you have impurities, and we'll represent that with triangles, those impurities can have or form defects in the crystal. Defects caused by impurities. Okay. And then obviously from those pictures, we have also a lot of impurities coating the solid, coating the crystals. Now you understand from general chemistry, you've heard of freezing point, same as melting point, depression. So impurities lower the melting point, typically, because the crystal structure is not as strong. The intermolecular forces are not as ordered. So impurities lower the melting point. Okay, so what's the technique of recrystallization? You add a solvent, and we'll make it green, and your crystals should still sink and still be insoluble in the solvent. So let me just represent that a little bit here. And you have your solvent. But this is at room temperature, RT. Can you visualize the beaker? Let me draw the beaker. The idea here is that you're going to heat it. Either heat the whole beaker or add hot solvent. And you're going to dissolve everything. And hopefully everything is dissolved. You want, ideally, a homogeneous solution where everything is now separated, the solute or the product, from all of these impurities. Now, theoretically, you should have more product molecules than impurities, and that's what I'm trying to show here, with more blue squares than pink triangles. The next thing is you either take it off the heat or stop adding hot solvent, and you're going to cool. And what's important is that you cool slowly. I'll tell you why in just a bit. And where am I going to draw this? Let me try to draw it here. As you cool slowly, your product molecules are going to find each other and start to adhere to each other. But the impurities will be excluded, like I set up here, and they will stay in solution. Now, that typically happens if you don't have a lot of impurities. If you have a lot more product molecules than impurities, then you hopefully expect or get this. Okay, crystals at the bottom or precipitate at the bottom. So these are either precipitate, or the precipitate can be in the form of crystals. That's an abbreviation, cross, tals. And again, impurities stay soluble. Next is filtration. So you're going to take this solution and you're going to filter it. What kind of filter do I want to use? Let's use a Buchner funnel. So what a Buchner funnel does is, and it could be vacuum also, vacuum filtration, but gravity works just as well in most cases, is that trapped in the filter paper, you'll have these crystals or precipitate, and going through the funnel, you have your impurities in the solvent. Now, danger. What happens if you cool too fast? If you cool too fast, instead of letting this come to room temperature slowly on the bench top, what if you plunge this beaker into ice water? If you cool too fast, the crystals form fast. And when that happens, you might trap impurities again, and you're back where you started. Trap impurities. Okay. That is the procedure in cartoon form of recrystallization. The next thing I want to discuss, part B, is requirements for this solvent. What makes a good solvent? I'll put it here. B. There are 4 requirements that make a good solvent. Now, it's not going to be, a lot of times, going to be perfect, but this is idealized. If you could find a solvent that does these 4 things, that's great. First of all, the crude product is insoluble in the solvent at room temperature. Right there. Solvent insoluble at room temperature. Because if it was soluble at room temperature, then you'll never be able to get out the crystals, even if you cool it. Okay, you want this to be insoluble at room temperature. It would be great, actually, if your product is insoluble and your impurities are kind of soluble. But we'll take care of that when we heat. That's required number 1. Required number 2 is, yes, when you heat, everything is soluble or near soluble. It's soluble or near soluble. Again, it's not going to be perfect, but hopefully all your impurities can be released in the hot solvent, just like this. Number 3, when cooled slowly, you get back the precipitate, because that would be tragic. If you cool and you get nothing back, there's no precipitate, then, oh gosh, your product is now soluble in solvent even when it's cold, cool or cold. But we'll go over some tricks to induce crystallization in part C. But ideally, when you cool slowly, crystals or precipitate form. Is there a difference between crystals and precipitate? When I think of precipitate, I think of like a powder or chunks of solid. Not very, well, crystals are also precipitate, but crystals are a specific type of precipitate where you have these very sharp edges, flat faces, rods maybe of crystals. Okay, next and last, 4. Oh yeah, it would be good if the solvent had a low boiling point. Because after you filter it, you've got to air dry it. So if the solvent's boiling point is very high, it will be very hard to air dry. We want a solvent that has a low boiling point so it can easily air dry after filtration. Those are the 4 requirements for recrystallization. Now, just a little trick. You could have solvent mixtures to try to match these requirements. It doesn't have to be a pure solvent. You can use solvent mixtures to modulate the polarity. By modulating the polarity, you can change the solubility of a solid in cold or cool or room temperature or hot solvent. You could tune it. Some ideas could be something like acetone. There's some mixtures that I've used in the past. Acetone in water, okay, mostly water, and then also ethyl acetate. That's 2 words in hexane, and in this case also mostly hexane, a little bit of ethyl acetate. Last thing I want to talk about is what happens, and it happens quite a bit, that when you cool slowly and the solution is now at room temperature and you see nothing. You don't get any precipitate. Basically, you see this, and by this I mean the solution is clear. You can see through it because there's no powder, no cloudiness, no precipitate. Okay. What happens when you cool and your solution is clear? You have to induce crystallization. Let me show you 4 ways to induce crystallization. So while this is 4 requirements of a good solvent, let me show you 4 ways, or tell you 4 ways to induce crystallization. This is C. Four ways to induce crystallization. A lot of work has been expended, and when you get to a point where you see no precipitate, it gets a little bit frustrating. But don't worry, your product's in there. We just have to coax it out of solution somehow, convince it to come out. So the first way is, we'll call it number 1. Try to concentrate the solution by evaporating some solvent. Try to concentrate solution by evaporating some, not all, solvent. If you evaporate all the solvent, what's the purpose of that? We're not going to have any liquid to filter to carry out the impurities. We need liquid still there. We can't evaporate all the solvent. But at least by making it more concentrated, we give the precipitate a better chance to come out. We give the product a better chance to form crystals because it's now a little more concentrated. That's number 1. Number 2, cool the solution. The procedure says to cool it slowly to room temperature, okay, just by letting it sit on the bench. But I want to cool the solution by putting the beaker in ice water. By putting the beaker in an ice water bath. Okay. You know that solids are typically less soluble in cold liquid. Normally you want to heat up. For instance, when you want to dissolve sugar in tea, you want to use hot tea, get all the sugar dissolved. Here we go the opposite. If we cool it, maybe we could convince the molecules to precipitate. Number 3, add a seed crystal. So this one's interesting. Where are you going to get a seed crystal? Well, maybe another group in the lab got crystals. Ask them for 1 or 2 seed crystals. Because what you can do is if you put a seed crystal in this situation here, after it's cooled, the seed crystal will give the other product molecules a surface to start nucleation. Let me write all of that down. Add a seed crystal to give dissolved product it's important that the seed crystal obviously matches the product that you're trying to precipitate. Because like molecules will help precipitate like molecules. So to give dissolved product molecules a similar surface to start nucleation. Nucleation is a little piece of the precipitate that helps recruit other molecules in the solution to start adhering or to start organizing around that nucleation site or that seed crystal. Number 4 and last one. This one's also strange at first. Scratch the inside of the beaker with a glass rod. Gotta be careful. You don't want to put so much pressure that you break the glass rod or you break the beaker, but you want to hear it. You want to hear it like nails on a chalkboard almost, because we want to create a rough surface. For crystals to adhere to. For tiny crystals to adhere to. And that will start the nucleation process to nucleate larger crystals or the growth of larger crystals. Okay, those are 4 ways to induce crystallization. If you don't get any crystals or precipitate when you cool to room temperature slowly. And typically, actually, after you cool slowly and you do get precipitate, I still recommend that my students put their beaker into some ice water to help precipitate as much as possible. Alright, so that's all I want to say about recrystallization. While I will not show you the recrystallized eugenol benzoate here, right? I want my students to discover what crystals of eugenol benzoate look like when they do this recrystallization. I do want to leave you with one video, 15 seconds, of a recrystallization. This is a recrystallization of acetylsalicylic acid, which is aspirin. And did I even start play? Okay. It's sped up, but you see that white, really shiny crystals form. These are pretty fine. So ideally, after the crystals have formed, you still want liquid, and there is liquid there, it just looks full, but there is liquid there by which you can do a filtration, and the liquid will carry out the impurities while the filter paper will trap your pure product. Alright, good luck with your own recrystallization, and don't forget those 4 tricks just in case you don't get any precipitate once the solution has cooled to room temperature.